What if everything you perceive, the solid ground beneath your feet, the stars above, even the flow of time itself, isn't quite as real as it seems? What if reality, as we know it, is just a fragile illusion, a thin veil draped over something far stranger and more incomprehensible? These aren't just questions for late-night philosophy debates. They're at the heart of some of the most groundbreaking theories in science and metaphysics today. From the holographic principle to simulation theory, the nature of reality is being questioned, tested, and reimagined in ways that challenge everything we thought we knew. And that's exactly what we're diving into today: 30 mind-bending theories that could rewrite our understanding of existence itself. Think about the last time you looked at a reflection in a mirror. It feels real, tangible, until you reach out and touch the glass, realizing it's just an illusion, a trick of light. Now, imagine that same principle applies to the entire universe. What if the cosmos we see is merely a projection, a shadow of a deeper, hidden reality? Scientists and philosophers have spent centuries unraveling these mysteries, and the answers they've uncovered, or at least theorized, are more astonishing than fiction. Some suggest we're living in a cosmic simulation, lines of code in an unfathomably advanced computer. Others argue that time is an illusion, that past, present, and future exist simultaneously in a vast, unchanging block. And then there are the theories that propose multiple realities, branching endlessly like an infinite tree of possibilities. This isn't just abstract speculation, it's a journey to the very edge of human understanding, where science and imagination collide. Each of these 30 theories offers a different lens through which to view reality, and together they paint a picture of a universe far stranger, more mysterious, and more wondrous than we ever dared to dream. So, if you've ever stared up at the night sky and wondered what's really out there, or questioned the nature of your own existence, you're in the right place. Because by the time we're done, nothing, not even the fabric of reality itself, will look quite the same. What if you woke up one day and discovered everything around you, the people you love, the places you've been, even your own memories, were nothing more than lines of code in an unfathomably advanced simulation? This is the core question behind the simulation hypothesis, one of the most provocative theories about the nature of reality. At its heart, the idea suggests our entire universe might be an artificial construct, a digital playground built by a civilization so advanced their technology is indistinguishable from what we'd call magic. Philosopher Nick Bostrom laid the groundwork for this theory with his now famous trilemma. He argued that at least one of 3 possibilities must be true. Either virtually all civilizations at our level of technological development go extinct before they can create advanced simulations, or no civilization ever reaches the capability or desire to run such simulations, or we are almost certainly living in one. If even a single advanced civilization chose to create simulated realities, and those simulations could eventually create their own, the number of artificial universes would vastly outnumber the real one. Statistically, the odds tilt heavily toward us being inside one of those simulations. Tech mogul Elon Musk has famously championed this idea, arguing that the rapid advancement of video game graphics and virtual reality suggests we're on the path to creating our own hyper-realistic simulations. If that's the case, he reasons, the likelihood that we're the original civilization, the one that cracked the code first, is astronomically slim. But the simulation hypothesis isn't just confined to philosophers and billionaires. Some scientists have explored ways to test it, looking for potential glitches in the fabric of reality, strange anomalies that could hint at underlying code. Have you ever experienced déjà vu, that eerie feeling you've lived a moment before, or noticed strange coincidences that seem too perfect to be random? Some proponents of the simulation theory point to these moments as possible evidence of a system processing data, like tiny hiccups in the program. Others speculate that quantum mechanics, with its bizarre particles that exist in multiple states until observed, might reflect the universe's rendering process, an optimization trick to save computational power. Of course, critics argue there's no concrete proof, just intriguing speculation. Some physicists counter that simulating an entire universe, down to the last atom, would require more energy than exists in, well, the universe. Others question why any civilization would bother creating such an elaborate simulation in the first place. But whether you find the idea exhilarating or unsettling, the simulation hypothesis forces us to confront profound questions about existence, purpose, and the very nature of what we call real. And if it's true, well, that might just be the most astonishing plot twist in the history of everything. Imagine holding a credit card in your hand, flat, thin, seemingly simple. Now picture every bit of information about your life, your memories, even the entire universe somehow encoded on its shiny surface. That's the essence of the holographic principle, a theory so radical it suggests our three-dimensional reality might just be an incredibly detailed projection from a two-dimensional surface at the edge of the cosmos. This mind-bending idea traces back to physicist Leonard Suskind's work on black holes in the 1990s. When matter falls into a black hole, classical physics says it's gone forever, vanished from our universe. But this clashes with quantum mechanics, which insists information can never be destroyed. Susskind and Dutch physicist Gerard T. Hooft proposed a solution. What if all the information about what falls into a black hole isn't lost, but encoded on its event horizon, the point of no return? Think of it like cosmic fingerprinting. Every atom, every photon leaves a trace on this two-dimensional boundary. But here's where it gets wild. If this holds true for black holes, could the same principle apply to the entire universe? Some theorists argue yes. They suggest that everything we experience, the stars, the oceans, even the sensation of wind on your skin, might be a holographic projection from a vast, flat membrane at the edge of space-time. It's as if the universe is an immeasurably complex movie, and we're not just watching it, we're the characters inside, unaware the screen exists. Recent experiments with quantum gravity have added fuel to this fire. Scientists studying the fabric of space-time at tiny scales have found unexpected correlations between surface areas and volumes, hints that information might indeed be stored in two dimensions, then rendered into the three-dimensional world we perceive. Other research has detected a mysterious pixelation in space-time itself, like the graininess you'd see if you zoomed way in on a digital image. Could this be the universe's underlying resolution, the signature of its holographic nature? This theory doesn't just challenge our everyday intuition, it upends centuries of physics. Newton and Einstein pictured a smooth, continuous universe, but the holographic principle suggests reality might be more like a mosaic, with each tiny tile carrying a fragment of the whole. It bridges the gap between quantum mechanics and gravity, two frameworks that have stubbornly refused to unite. And if proven true, it would mean that everything from the swirling galaxies to the thoughts in your head is fundamentally information written on the cosmic equivalent of a DVD. So why does any of this matter? Because if the holographic principle is correct, it reshapes what we think is possible. Time and space might not be the unchanging stage of reality, but dynamic, emergent properties, like ripples on the surface of something far deeper. It opens doors to technologies we can't yet fathom, like manipulating reality by rewriting its underlying code. And most profoundly, it hints that the universe isn't just something we observe, it's something we're intimately, holographically woven into. What if every choice you've ever made, every path taken, every word left unspoken existed simultaneously in countless other realities? This is the staggering promise of multiverse theory, the idea that our universe isn't alone but just one page in an infinite cosmic library of parallel existences. While it sounds like science fiction, this concept has deep roots in quantum mechanics and cosmology, offering explanations for some of the universe's greatest mysteries. Take quantum mechanics, where particles exist in multiple states until observed, a phenomenon called superposition. In the 1950s, physicist Hugh Everett proposed his controversial many worlds interpretation. What if every possible outcome of a quantum event isn't just theoretical but actual? When you measure a particle, the universe doesn't randomly pick a state, it splits. One version of you sees the particle spin up, another version in a branching timeline sees it spin down. Over time, these splits multiply exponentially, creating an ever-growing tree of realities where every conceivable possibility plays out. It means there's a universe where you took that job overseas, another where dinosaurs never went extinct, and one where your childhood goldfish lived to be 20. But quantum branching isn't the only path to multiple worlds. Cosmic inflation theory suggests that in the first fractions of a second after the Big Bang, space expanded faster than light, creating vast bubble universes. Like soap suds in a sink, these bubbles might each have their own physics, some with stronger gravity, others where time runs backward. Our observable universe could be just one bubble in an unimaginably vast cosmic froth. Pop culture loves this idea. Films like Doctor Strange show heroes hopping between realities, while novels like Dark Matter explore the emotional weight of roads not taken. But beyond entertainment, multiverse theory solves puzzles. Why does our universe seem fine-tuned for life? If infinite variations exist, it's no surprise one got the numbers right. Yet critics argue this makes the theory untestable by definition. If other universes are forever beyond our reach, does multiverse theory cross from science into philosophy? Some physicists search for bruises in our universe, odd voids in space, or unexplained temperature variations. That might be cosmic collisions with other bubbles. Others look for quantum echoes, subtle patterns in particles that could hint at branching timelines. Whether it's ultimately proven or not, multiverse theory reshapes how we view existence. It suggests that somewhere out there, every version of you is living every possible life, an idea as humbling as it is exhilarating. The question isn't just whether other universes exist, but what it means about our place in the grand scheme of things. Picture floating alone in an endless void, no stars, no planets, just emptiness stretching forever. Now imagine that in this infinite darkness, by sheer random chance, atoms suddenly arrange themselves into a fully formed conscious brain. Not attached to a body, not born from evolution, but spontaneously emerging from chaos with all your memories, thoughts, and sensations intact. This unsettling thought experiment is the essence of the Boltzmann brain hypothesis, a concept so bizarre it keeps cosmologists awake at night. The idea traces back to 19th century physicist Ludwig Boltzmann, who revolutionized our understanding of entropy, the tendency of systems to move from order to disorder. He realized that in an infinitely old universe, even the most improbable events must eventually happen. Given enough time, monkeys randomly typing could produce Shakespeare, and atoms jostling in space could briefly assemble into a thinking mind. Modern cosmology amplifies this paradox. If our universe truly lasts forever, as some theories suggest, then statistically, these random, self-aware flashes Boltzmann brains should vastly outnumber ordinary, evolved minds like ours. Here's where it gets eerie. If you woke up right now, how could you prove you're not one of these random, momentary constructs? Every memory, every scrap of knowledge about the world could just be a fluke illusion cobbled together by chaotic atoms. Some scientists argue this makes Boltzmann brains a fatal flaw in certain cosmological models. If the math predicts the universe should be teeming with disembodied minds rather than stable civilizations, maybe our models are missing something fundamental. Critics counter that Boltzmann brains are less a serious theory and more a reductio ad absurdum, a way to expose weaknesses in assumptions about eternal universes. After all, we observe a cosmos filled with galaxies, planets, and life, not drifting brains. This discrepancy hints that our universe might have a finite timeline or an underlying mechanism preventing such chaos-born consciousness. Yet the puzzle lingers, forcing us to confront profound questions. What does it mean to be real in a universe governed by probability? Are we the rule or the astronomically unlikely exception? Boltzmann brains don't just challenge cosmology, they blur the line between reality and statistical mirage, leaving us wondering if even the ground beneath our feet is as solid as it seems. What if time, the steady, unshakable rhythm of your life, is nothing more than a convincing illusion, not just a human construct like hours or minutes, but the very flow of cause and effect itself? This radical idea isn't science fiction. It's a serious challenge emerging from the frontiers of physics, where some researchers argue time might not be a fundamental feature of reality at all. Take Julian Barber's controversial timeless physics. He paints a universe where every moment exists eternally, frozen like frames in a film reel. In this view, what we call time is just our brain stitching together static snapshots, the way flipping through a stack of photographs creates the illusion of motion. Barber's universe has no past pushing the present into the future. Instead, every possible configuration of particles, every now, exists simultaneously in a vast landscape he calls Platonia. Your sense of moving through time, just a trick of perspective, like standing in a hall of mirrors and mistaking reflections for motion. Carlo Rovelli, a pioneer of loop quantum gravity, offers a different twist. He proposes time isn't absolute but relational, a measure of how objects interact, not some universal backdrop. Think of it like a cosmic game of dominoes. Events only happen when one domino tips into another. Without those connections, there's no meaningful sequence. This explains why time behaves strangely near black holes or at quantum scales. It's not a river flowing everywhere equally, but a patchwork of local interactions. A clock on a satellite ticks differently than one on Earth, not because time itself changes, but because the relationships between particles do. Dig deeper into quantum gravity theories, and time's foundations crumble further. In experiments with ultra-cold atoms, scientists can create frozen quantum states where particles stop evolving entirely, like hitting pause on reality's movie. Some equations describing quantum fields work perfectly if you mathematically erase time, suggesting it might be an emergent property, like temperature arising from the motion of molecules. Even spacetime, the interwoven fabric Einstein described, may dissolve at the tiniest scales, leaving only abstract mathematical relations. So why does time feel so real? Evolution likely hardwired us to perceive sequence and cause because it helped our ancestors survive. But just as a fish doesn't perceive the water it swims in, we might be blind to time's true nature. If these theories hold, it reshapes nothing less than our understanding of existence. No beginnings, no endings, just an intricate web of nows we're wired to experience as flow. The past and future wouldn't vanish, they'd simply be places we aren't currently looking, and that strange feeling when déjà vu hits, maybe, just maybe, it's a fleeting glimpse behind the curtain. What if consciousness isn't something that emerges from complex biology, but is instead woven into the fabric of the universe itself, a fundamental property of reality like space or time? This is the bold claim of panpsychism, a theory that's equal parts ancient wisdom and cutting-edge philosophy. Unlike traditional materialism, which treats consciousness as a byproduct of brains, panpsychism suggests that even the smallest particles might possess some rudimentary form of experience. Picture an electron not just as a mindless speck of matter, but as something with an infinitesimal inner life, a faint hum of subjectivity. The idea isn't new. Philosophers like Plato and Spinoza toyed with variations of it, while indigenous cosmologies have long described rocks, rivers, and storms as imbued with spirit. But modern thinkers like Galen Strawson have revived panpsychism with rigorous arguments. framing it as the least absurd solution to the hard problem of consciousness. That problem, coined by David Chalmers, asks why and how physical processes in the brain give rise to subjective experience, the redness of red, the sting of pain. Materialism struggles to explain this gap, but panpsychism flips the script. If consciousness is elemental, then brains don't create it, they amplify and organize it. Critics dismiss this as mystical thinking, asking how inanimate matter could feel anything. But panpsychists counter that dismissing it outright begs the question. After all, science assumes matter has intrinsic properties, charge, mass, so why not some proto-consciousness? Some theories even link it to quantum phenomena, suggesting that the collapse of a particle's wave function might involve a tiny act of choice. Where the theory truly shines is in its elegance. Just as gravity operates at all scales, from apples falling to planets orbiting, panpsychism proposes consciousness scales up from atoms to animals. In this view, your mind isn't a miracle, it's a symphony of trillions of tiny experiences harmonized by evolution. Yet mysteries remain. How do micro-experiences combine into a unified thought? Does a thermostat have a fleeting sensation of temperature? Whether panpsychism is poetic speculation or profound insight, it challenges our anthropocentrism, hinting that the universe might be far more alive than we ever imagined. And if true, it means every star, every stone, even the void between galaxies, hums with some ineffable whisper of being. What if the universe isn't just described by mathematics but actually runs on it? An immense, self-executing program where every event, from the birth of stars to the firing of neurons, is just lines of code in a cosmic algorithm. This is the spine-tingling premise of digital physics, a theory that merges computer science with cosmology to suggest reality isn't merely like a computation, it fundamentally is one. The roots of this idea stretch back to Konrad Zuse, the German engineer who built the first programmable computer in the 1940s. While wiring his Z3 machine, Zuse had a radical thought. What if the universe itself operates on discrete, computational rules? He proposed that space could be a grid of finite cells like pixels on a screen, each updating its state based on mathematical operations, a cosmic version of the binary logic powering his inventions. Though his peers dismissed it as whimsy, Zuse's calculating space hypothesis planted the seed for a revolution. Decades later, physicist Edward Fredkin took this further with his theory of digital ontology. Fredkin argued that information isn't just a tool for understanding reality, it is reality. Atoms, forces, even time itself might be manifestations of deeper, immaterial bits flipping beneath the surface. Picture the universe as an infinite chessboard where each square follows simple rules, yet their collective interactions generate the dizzying complexity we see. Fredkin's most startling claim, that there's no true randomness, only calculations so vast they feel unpredictable, like a movie rendered frame by frame in real time. Evidence for this wild idea comes from unexpected places. Take cellular automata, simple programs where grids of cells evolve via basic rules. The most famous, Conway's Game of Life, proves how astonishing complexity can emerge from humble beginnings. Gliders that move, patterns that replicate, even structures that mimic logic gates. If a two-dimensional grid can simulate computation, could the universe's three-dimensional lattice be doing the same? Some physicists point to quantum mechanics, where particles exist in defined states only upon measurement, as potential rendering of a deeper computational process. But digital physics doesn't just reshape our view of space, it redefines mathematics itself. Is math a human invention or the universe's native language? Max Tegmark's mathematical universe hypothesis takes this to the extreme, proposing that every self-consistent mathematical structure physically exists. In this view, our cosmos isn't running on math, it is math, one instance in an infinite library of equations playing out as realities. critics argue this veers into metaphysics. If everything's computation, what's running the program, and why assume reality is digital rather than analog? Yet the theory's elegance is undeniable. It unifies the granularity of quantum physics with the determinism of relativity, suggesting that beneath the chaos, the cosmos ticks with the precision of a master algorithm. Whether you find it inspiring or unsettling, digital physics forces a profound question. If reality is code, who or what wrote it? And are we merely characters in the script or something stranger, lines of the program becoming aware of itself? Picture standing on a quiet street at dusk, watching cars pass by. Each vehicle exists at a different point along the road, some nearing you, some receding, all equally real despite occupying separate spaces. Now imagine if time worked the same way, not as a flowing river carrying us from past to future, but as a vast, unchanging landscape where every moment, your first breath, your last thought, and everything in between exists simultaneously, eternally. This is the spine-tingling vision of eternalism, the idea that time is a dimension much like space, and what we call now is merely a matter of perspective. At its core, eternalism comes straight from Einstein's theory of relativity. His equations revealed that time isn't universal, it stretches and compresses depending on motion and gravity. But more startlingly, they showed that past, present, and future are woven together into a single structure, the block universe. Think of it as a cosmic loaf of bread, where each slice is a moment in time. From a God's eye view outside the loaf, everything is equally real: the Big Bang, the fall of Rome, your birth, and the heat-death of the universe all exist at once, like frames in a film reel stacked and waiting to be observed. This flips everyday intuition on its head. We experience life as a relentless march forward, but eternalism suggests that's an illusion, a trick of consciousness. Just as a DVD contains an entire movie while the laser reads only one scene at a time, the block universe holds all of history, while our awareness scans through it moment by moment. This raises thorny questions about free will. If the future is already out there, fixed in the block, are our choices truly free? Some philosophers argue yes, our decisions still shape which paths become real for us, like hikers carving routes through an endless mountain range. Others see it as proof that freedom is a comforting myth, and every action was predetermined the moment the universe began. Eternalism's rival, presentism, fiercely disagrees. This view insists only the present exists, the past is gone, the future unborn, and reality is an ever-shifting now. It aligns with how we instinctively perceive time but clashes with relativity. If two astronauts pass each other at near light speed, their watches tick at different rates. Whose now is real? Einstein himself concluded that the distinction between past and future is only a stubbornly persistent illusion. The implications stretch beyond physics. If eternalism holds, then death isn't an erasure, it's just a coordinate in the block. Your happiest memories don't fade, they persist forever in their own slice of space-time. It's a notion both comforting and eerie, suggesting that somewhere in the grand architecture of reality, you're always laughing with old friends, always taking your first steps, always staring up at the stars and wondering, just as you are now. Yet the debate rages on. Does time flow, or is flow a trick of the mind? Is the universe a story unfolding, or a completed book we're reading one page at a time? Eternalism doesn't just challenge clocks and calendars, it forces us to rethink what it means to exist at all. And if it's true, then somewhere in the block, you're already watching this video again, marveling at how reality isn't quite what it seems. What if death, that inevitable end we all fear, wasn't actually inevitable for you, at least? This is the unsettling promise of quantum immortality, a thought experiment so bizarre it makes parallel universes seem mundane. Imagine you're playing a deadly game of Russian roulette with a twist. The gun is quantum linked, meaning each trigger pull creates a branching reality where the gun either fires or doesn't. In some timelines, you die instantly, but from your subjective perspective, you'd always find yourself in a branch where the chamber was empty, no matter how many times you pull the trigger. You'd never experience death, only increasingly improbable survival. This idea springs from the many worlds interpretation of quantum mechanics, where every possible outcome spawns a new universe. Max Tegmark, a vocal proponent, frames it mathematically. If consciousness is tied to quantum states, your awareness would always follow the path where you remain alive. It's Schrödinger's cat with a morbid upgrade instead of a feline in a box. It's you forever observing yourself as the lucky version who never meets an end. Even if Earth exploded, there'd theoretically be a universe where you, against all odds, somehow survived. But quantum immortality isn't just a physics puzzle, it's an ethical minefield. If the theory holds, would reckless behavior be rewarded with endless near-death escapes? Could dictators or criminals persist indefinitely in branching realities? And what about aging? Some interpretations suggest you'd inevitably find yourself in timelines where medical breakthroughs extend your life unnaturally, leaving you a conscious observer in a body that, by all rights, should have perished centuries ago. Critics pounce on the theory's unfalsifiability. If you can't observe the branches where you die, how could you ever prove it? Others argue consciousness isn't quantum linked at all, making the whole premise a flawed metaphor. Yet the idea lingers, forcing us to confront uncomfortable questions about identity, probability, and whether our sense of self is more fragile or more resilient than we ever imagined. After all, if you suddenly found yourself the sole survivor of a plane crash, would you call it a miracle or just quantum statistics playing out? The line between science and survival instinct has never felt so thin. Thousands of years before quantum physicists grappled with the nature of reality, ancient Hindu sages were already describing the universe as an elaborate illusion, a cosmic magic trick called Maya. This isn't just poetic metaphor, it's a sophisticated philosophical framework suggesting that the world we perceive is merely the surface layer of a deeper, unified reality. Imagine watching a movie so immersive you forget you're in a theater until the credits roll, and you remember the screen was just flat all along. Maya proposes we're all living in that cinematic trance, mistaking the projection for ultimate truth. At the heart of this idea is Advaita Vedanta, the non-dualistic school championed by the philosopher Adi Shankara in the 8th century. He taught that Brahman, the infinite, unchanging reality, is the only true existence, while the fleeting world of forms and names is Maya's shimmering veil. Think of it like waves on an ocean. The waves appear distinct, but they're fundamentally just water. Similarly, your body, thoughts, and the stars above aren't separate things, but temporary expressions of one boundless consciousness. The goal of life, in this view, isn't to navigate the illusion, but to awaken from it, to realize tat tivam asi. You are that, the thunderous truth that observer and observed are one. What's astonishing is how these ancient insights echo cutting-edge physics. Quantum entanglement, where particles instantly influence each other across vast distances, mirrors Advaita's claim that separateness is an illusion. The observer effect, where measuring a particle changes its state, aligns with yogic teachings that consciousness shapes reality. Even the holographic principle's suggestion that information encodes our three-dimensional world parallels Vedic descriptions of reality as vibrational patterns in a divine mind. Yet Maya isn't nihilistic, it's transformative. Unlike Western materialism, which often reduces consciousness to brain chemistry, Hinduism's illusion carries purpose. Maya is the divine's play Leela, a way for the absolute to experience its own creativity. Ramana Maharshi, a modern sage, compared it to a rope mistaken for a snake in dim light. The fear is real until dawn reveals the truth. Spiritual practice, then, isn't about rejecting the world but seeing through its fleeting nature to the stillness beneath. modern spiritual movements have adapted these ideas, sometimes controversially. New Age interpretations often simplify Maya as you create your reality, blurring the line between ancient wisdom and self-help optimism. Meanwhile, neuroscientists like Carl Friston explore predictive coding, how the brain constructs perception, finding eerie overlaps with Advaita's view that the mind projects reality rather than passively receiving it. The tension with Western materialism is stark. Science seeks to explain consciousness by dissecting the brain. Vedanta suggests the brain is part of the illusion to be transcended. One asks, how does matter create mind? The other counters, what if matter is the mind's dream? This isn't just philosophical sparring, it reshapes how we approach existence. If life is Maya, suffering loses its teeth when seen as passing drama, and joy becomes not a pursuit but a homecoming. Whether you see Maya as profound truth or poetic speculation, its endurance across millennia hints at something primordial in the human psyche. After all, haven't you ever felt in quiet moments that the world might be more and less than it seems? That behind the curtain of daily life, something luminous waits, patient and unchanging. What if you're the only real thing in the universe and everything else, your friends, your home, even the stars, are just figments of your imagination? This is the radical premise of solipsism, the philosophical stance that only one's own mind can be known to exist with certainty. It's the ultimate skepticism, a lonely island where you're both the prisoner and the warden of reality. The roots of this idea trace back to René Descartes, the 17th century thinker who stripped away all assumptions in his quest for undeniable truth. His famous declaration, "I think, therefore I am," was the one bedrock he couldn't doubt. Even if an evil demon were deceiving him about everything, the act of doubting proved something was doing the doubting. But here's the twist. Descartes used this as a starting point to rebuild knowledge, while solipsism takes it as the end of the road. If all you can truly know is your own consciousness, then the entire external world becomes a question mark. Modern twists on this notion include the brain in A Vat scenario, a favorite of philosophers and sci-fi writers alike. Picture a mad scientist keeping your brain alive in a tank, feeding it fabricated electrical signals that mimic a full, rich life. How could you ever prove this isn't the case? The Matrix films run with this idea, showing humans trapped in a simulated world, unaware their bodies are dormant in pods. But solipsism goes even further. What if there's no pod, no simulation, just you conjuring reality from nothing? The unsettling power of solipsism lies in its unfalsifiability. You can't disprove it because any evidence you'd use, other people's testimony, scientific instruments, could itself be part of the illusion. It's like trying to use a dream character to confirm you're awake. Even the laws of physics might just be rules your mind imposes on its own hallucination. Pop culture loves to toy with this existential vertigo. Films like The Truman Show and Inception explore what happens when reality's walls start to crack, while novels like Ubik by Philip K. Dick blur the lines between perception and delusion. These stories resonate because they tap into a primal fear. What if the world isn't just misunderstood but fundamentally unreal? Yet solipsism isn't just a thought experiment, it's a mirror. However logically airtight it may seem, most of us feel the reality of other minds. When a friend laughs or a stranger winces in pain, we don't experience them as elaborate puppets. Evolution likely hardwired us to assume an external world because it kept our ancestors alive. But that doesn't resolve the philosophical itch. Critics argue solipsism is sterile. It can't be proven or disproven, so it offers no practical value. Others see it as intellectually arrogant, a dismissal of shared human experience without justification. Yet even as we reject it in daily life, solipsism lingers as a ghost in the machine, reminding us that reality's foundations are shakier than they appear. After all, if you can't be sure of anything beyond your own thoughts, what does that say about the nature of existence itself? The answer might be simple: nothing or everything. Imagine zooming in on the fabric of space so closely that instead of a smooth, unbroken surface, you see a shimmering network of interconnected loops, a cosmic spiderweb woven from the tiniest possible stitches of reality. This is the breathtaking vision of loop quantum gravity, a daring theory that rewrites Einstein's spacetime as a granular, pixelated structure at the smallest scales. While string theory dominates headlines with its tiny vibrating strings, loop quantum gravity takes a radically different path, proposing that space itself is quantized, not continuous, but built from finite, indivisible building blocks. At the heart of this idea is physicist Carlo Rovelli, who helped pioneer the theory in the 1990s. His work suggests that space isn't an empty stage where matter plays out its drama, but a dynamic tapestry of spin networks, intertwined loops of gravitational field lines. These loops aren't floating in space, they are space. Picture a mesh of interconnected threads where each knot represents a vanishingly small volume, about 10 to the minus 35th meters across a scale so tiny it makes atoms look like galaxies. Time in this framework emerges from the changing relationships between these loops, like the ticking of a cosmic clock made of shifting connections. One of loop quantum gravity's most startling predictions is the eradication of singularities, those infinitely dense points at the center of black holes where Einstein's equations break down. Instead of a crushing, inscrutable endpoint, the theory suggests that matter collapsing into a black hole would eventually rebound like a spring compressed to its limit. This big bounce could even apply to the birth of our universe, implying the Big Bang wasn't a true beginning, but the resurgence of a prior cosmos. It's as if the universe itself is cyclical, breathing in and out across eons. Yet for all its elegance, loop quantum gravity faces steep challenges. Unlike string theory, which aims to unify all fundamental forces, this framework focuses squarely on gravity and quantum mechanics. That specialization gives it clarity but leaves gaps, like explaining how particles acquire mass or why the universe has the precise constants it does. Experimental verification is another hurdle. Probing the Planck scale requires energies trillions of times beyond what our particle colliders can achieve. Some researchers hunt for indirect clues, like subtle imprints in the cosmic microwave background or anomalies in gravitational waves that might betray spacetime's granular structure. Others look for quantum fluctuations in the speed of light, which could reveal the underlying pixels of reality. The debate between loop quantum gravity and string theory isn't just academic, it's a clash of philosophies. String theory imagines reality as vibrations in higher dimensions, while loop quantum gravity roots itself firmly in three-dimensional space, treating gravity as geometry's quantum dance. Both seek to heal the rift between general relativity and quantum mechanics, but their paths diverge like rivers carving canyons through bedrock. What makes loop quantum gravity so compelling isn't just its answers, but the questions it forces us to ask. If space is granular, does that mean there's a smallest possible distance beyond which movement becomes impossible? Could the universe's deepest layer be more like a vast, evolving equation than a collection of objects? Rovelli often compares it to Democritus' ancient insight that matter is made of atoms, an idea once ridiculed, now foundational. Perhaps one day we'll look back at smooth spacetime as we do at the flat Earth, a comforting illusion shattered by the brave who dared to peer deeper. Until then, the loops keep spinning, weaving the unseen fabric of everything. What if the trees, the stars, the very cosmos around you only exist because you're here to perceive them? This is the electrifying claim of biocentrism, a theory that flips traditional physics on its head by proposing that life isn't just a passenger in the universe, it's the architect. At its core, biocentrism argues that consciousness isn't a latecomer to the cosmic party, but the foundational force shaping reality itself. Forget the notion of an objective world out there. In this view, the universe is more like a grand symphony that only plays when observed, with living beings as both audience and composer. The modern architect of this idea, scientist Robert Lanza, draws striking parallels between biocentrism and the weirdness of quantum mechanics. Take the double-slit experiment, where particles behave as waves until measured, collapsing into definite states. To Lanza, this isn't just a quantum quirk. It's proof that reality requires an observer to crystallize from potentiality into existence. He takes it further by weaving in the anthropic principle, the unsettling precision of the universe's constants like gravity's strength or the mass of electrons that allow life to exist. To biocentrists, these aren't happy accidents but clues that reality is fine-tuned because consciousness is its ultimate purpose. Critics, however, pounce on biocentrism's bold dismissal of objective reality. If a tree falls in a forest with no one around, does it make a sound? Traditional physics says yes, sound waves propagate regardless of observers. But biocentrism implies the tree's very existence hinges on being perceived, a notion that rattles the foundations of empirical science. Renowned physicist Lawrence Krauss has called it poetic nonsense, arguing that the universe's history, like ancient starlight reaching us from billions of years ago, contradicts the idea that consciousness retroactively creates reality. Even quantum pioneers like Niels Bohr cautioned against conflating measurement-dependent phenomena with a universe conjured by mind alone. Yet biocentrism's allure persists, bridging ancient philosophies and cutting-edge science. Hindu texts describe Brahman as a cosmic consciousness dreaming the world into being, while Bishop Berkeley's 18th-century idealism claimed to be is to be perceived. Lanza's twist is grafting these ideas onto quantum biology, suggesting that processes like bird migration or photosynthesis might exploit quantum effects, hinting that life and the fabric of reality are deeply entangled. The theory's weakest link might be its reliance on the anthropic principle as explanation rather than puzzle. Just because the universe permits life doesn't necessarily mean life created it, any more than a puddle marveling at how perfectly its hole fits its shape proves the hole was designed for it. Still, biocentrism's audacity forces us to confront uncomfortable questions. Is science's quest for an observer-independent reality doomed? Or is the true mystery not how consciousness arose from matter, but how matter arises from consciousness? Whether you find it profound or provocative, biocentrism turns the universe into a hall of mirrors where the greatest reflection might be your own gaze, shaping everything it falls upon. What if the universe isn't built on atoms or energy, but on something far more fundamental, mathematics itself, not just as a language to describe reality, but as the very substance of existence? This is the audacious claim of the mathematical universe hypothesis, championed by physicist Max Tegmark, who argues that our cosmos isn't merely governed by math, it is math. Imagine peeling back layers of reality like an onion, past quarks and quantum fields, until you reach a realm where numbers and equations aren't tools but the bedrock of being. Tegmark's idea isn't entirely new. Over 2,000 years ago, the Pythagoreans whispered a similar heresy that all things are number. They saw musical harmonies as ratios, planetary motions as geometric dances, and believed the cosmos hummed with numerical perfection. Modern science seemed to validate their hunch. From the elegant simplicity of Newton's gravity to the uncanny precision of quantum equations, mathematics predicts phenomena with eerie accuracy, as if nature is dutifully following a hidden script. Tegmark takes this further. If a mathematical structure perfectly describes a universe, doesn't that mean the structure is the universe? Consider the Mandelbrot set, an infinitely complex fractal generated by a simple equation. Zoom into its spiraling edges and new worlds of detail emerge, yet it's all encoded in a few symbols. Now imagine every electron, galaxy, and thought in our universe is similarly rendered from abstract mathematical relationships. In this view, physics isn't the study of matter, but of numerical patterns that give rise to matter's illusion. Tegmark even speculates that every possible mathematical structure corresponds to a real physical universe, meaning there's a cosmos where triangles have four sides, gravity repels, and time flows backward. But does math exist independently like Plato's ideal forms, or is it a human invention, a useful fiction? Opponents like physicist Lee Smolin argue math is merely a map, not the territory, brilliant for modeling reality, but not reality itself. They point to gaps where math stumbles, like uniting quantum mechanics with gravity, as proof of its limits. Others counter that our mathematical blind spots might reflect our cognitive constraints, not the universe's. After all, octopuses experience color beyond human perception. Could undiscovered math lurk beyond our mental reach? The theory's biggest challenge is its blurring of science and metaphysics. If every equation spawns a cosmos, how could we test or falsify them? Tegmark suggests looking for unnecessarily complex math in our universe, signs we're in an unnatural simulation. But critics call this untestable speculation, veering into numerology. Yet the hypothesis's elegance is undeniable. It dissolves the mystery of why math works so well, because reality is math, and answers the haunting question of whether we're alone. In Tegmark's multiverse, every possible world exists, from the barren to the bizarre. Perhaps the most profound implication isn't about universes but meaning. If existence is just relationships between numbers, does that diminish wonder or heighten it? A rainbow isn't less beautiful because it's light refracted through prisms. Maybe reality is more astonishing as an eternal equation humming in the dark. Whether ultimate truth or elegant mirage, the mathematical universe hypothesis forces us to confront a radical possibility: that we're not just observers of the cosmos, but fragments of its deepest language equations that somehow learn to ponder themselves. What if the act of looking at a quantum particle doesn't just reveal its state? What if it creates it? This startling possibility lies at the heart of John von Neumann's controversial observer theory, where consciousness isn't just a passive witness to reality, but the very force that sculpts it from quantum fog. The Hungarian polymath, whose fingerprints are on everything from game theory to the atomic bomb, proposed that the collapse of a particle's wave function, the moment it chooses a definite position or spin, isn't triggered by detectors or lab equipment, but by the mind observing it. In this view, the universe exists in a shimmering superposition until consciousness steps in, like a spotlight freezing a dancer mid-motion. The implications grow even stranger with Eugene Wigner's thought experiment, known as Wigner's friend. Picture a physicist in a lab measuring a quantum system, say, the spin of an electron. To the physicist, the electron's wave function collapses the instant they observe it. But now imagine Wigner standing outside the lab, treating his friend and the entire experiment as one big quantum system. From his perspective, the physicist and the electron remain entangled in superposition until he looks. So who's right? Does reality solidify at the first observation, or only when some conscious being, perhaps a cosmic ultimate observer, finally takes notice? The paradox suggests there's no objective now, only layers of relative observation peeling back endlessly. Materialist physicists recoil at this idea. They argue quantum decoherence, the process where particles interact with their environment, leaking quantum weirdness into the surrounding chaos, explains wave function collapse without invoking consciousness. A photon hitting a detector doesn't need a mind to register. It just needs enough atoms bumping around to pin down its state. Critics like Sean Carroll dismiss von Neumann's view as quantum mysticism, insisting that consciousness emerges from physics, not the other way around. Yet the puzzle persists. Why does measurement have this magical power to collapse possibilities into facts? Even decoherence just pushes the question back: or what counts as a measurement in the first place? Quantum theorists have spent decades wrestling with these questions. Some, like Henry Stapp, suggest consciousness isn't magic but a physical process that integrates quantum information in the brain. Others propose that observation doesn't require human minds. Any sufficiently complex system could do the job, from a camera sensor to a leaf rustling in the wind. But von Neumann's original insight lingers like a ghost in the machine, whispering that the line between observer and observed might be the most fragile illusion of all. After all, if consciousness truly shapes reality, then the greatest scientific instrument isn't a telescope or collider, it's you. What if our entire universe, every galaxy, every atom, every moment of history, is just the swirling interior of a black hole from some grander cosmos beyond? This isn't the plot of a sci-fi novel, but a serious hypothesis called black hole cosmology, where the birth of our universe wasn't a singular Big Bang, but the explosive recoil of matter squeezed beyond limits in the heart of a collapsing star. Picture a Russian nesting doll, but instead of wooden figures, each layer is a universe inside a black hole, inside another universe stretching back infinitely. At the center of this idea is physicist Nikodem Poplawski, who proposed that when matter gets crushed to unimaginable densities inside a black hole, it doesn't just form a singularity, it rebounds. Think of a spring compressed to its absolute limit, then snapping back with enough force to birth an entire new spacetime. In this view, what we call the Big Bang might actually have been a white hole, the hypothetical opposite of a black hole where matter erupts outward instead of vanishing inward. It's as if our cosmos is the cosmic equivalent of a phoenix, born from the ashes of some long-dead star's catastrophic collapse. What makes this theory so compelling is how neatly it solves two of cosmology's biggest puzzles. First, dark energy, the mysterious force accelerating the universe's expansion. Poplawski's math suggests this could be a relic of our black hole origin, a kind of spin memory, imprinted by the rotation of the parent black hole, gently pushing spacetime apart like a whisper from another reality. Second, the perplexing uniformity of the cosmic microwave background, the afterglow of the Big Bang. Standard cosmology struggles to explain why distant regions of space have identical temperatures when they were never in contact. But if our universe inherited its structure from the orderly, high-energy crush inside a black hole, that smoothness might be baked in from the start. Of course, mainstream cosmologists aren't ready to abandon the traditional Big Bang model. They argue that black hole cosmology lacks direct evidence. We can't peer beyond the event horizon to check for baby universes. And while Poplawski's equations are elegant, they're hard to test. Yet the theory's audacity forces us to reconsider fundamental assumptions. If true, it means every black hole in our universe could be a cosmic womb, each harboring an entire spacetime within. The night sky wouldn't just be studded with stars, but with potential universes, each with their own physics, their own stories. The debate between these models isn't just academic, it reshapes how we see existence itself. Standard cosmology paints the universe as a one-time event, expanding toward heat death. Black hole cosmology offers a cyclical vision, where universes breathe in and out like lungs, each collapse birthing a new beginning. It's the ultimate cosmic recycling program, where even the darkest pits of space might cradle the seeds of light. And if you're feeling small in the grand scheme of things, consider this: somewhere beyond the veil of our reality, the universe that birthed ours might still be out there, unaware that within its darkest corners, we're asking questions about how it all began. Imagine a snowflake that not only repeats its intricate pattern in space, but in time, a structure as eternal as the ticking of a cosmic clock, cycling through its shapes without ever winding down. This is the mesmerizing promise of time crystals, a bizarre phase of matter that defies our everyday intuition about how the universe works. First proposed by Nobel laureate Frank Wilczek in 2012, these quantum curiosities don't just exist in three dimensions like ordinary crystals. They pulse rhythmically in the fourth dimension, time itself, creating a perpetual dance of order without energy. Wilczek's initial idea seemed to flirt with the impossible. In a universe governed by entropy, where everything tends toward disorder, how could anything exhibit periodic motion forever without violating the laws of thermodynamics? The key lies in quantum isolation. Unlike a pendulum which slows due to friction, time crystals exist in a delicate quantum state where their repeating patterns are locked into the fabric of reality. Think of them as the universe's metronome, never gaining or losing energy, just ticking in perfect, unchanging rhythm. The real shock came in 2017 when two separate teams, one at Harvard and another at the University of Maryland, actually built time crystals in the lab. Using chains of ytterbium atoms chilled to near absolute zero and hit with precisely timed laser pulses, they observed systems that cycled between states at intervals unrelated to the energy pumped in, a telltale signature of time symmetry breaking. It's as if you tapped a piano key every second, but the string insisted on humming its own melody, synchronized yet independent. What makes time crystals more than just a laboratory marvel are their staggering implications. For one, they hint at new states of matter we've never imagined, materials that could, in theory, hold coherent quantum information indefinitely, revolutionizing quantum computing. Even wilder is their potential to upend our understanding of time's arrow. Most physical processes are irreversible, but time crystals suggest that under the right conditions, the distinction between past and future might blur into something more fluid. Yet the most tantalizing possibility lies in their apparent defiance of equilibrium. Normally, systems settle into a steady state like hot coffee cooling to room temperature. Time crystals, however, never reach equilibrium. They're eternally out of step with the universe's march toward disorder. Some theorists speculate this could lead to genuine perpetual motion machines, not the fanciful devices of Victorian inventors, but quantum systems that harness subtle asymmetries in the laws of physics. Of course, skeptics caution that time crystals don't actually do work. They're more like cosmic clocks than engines. But their very existence stretches the boundaries of what we thought matter could achieve. If crystals can eternally mark time without energy input, what other impossible structures might be hiding in the quantum shadows? Perhaps one day, time crystals will tick inside our computers, our spacecraft, even our understanding of reality itself, silent, unchanging, and utterly alien, like fragments of a deeper physics waiting to be decoded. What if the secret to consciousness isn't buried in the complexity of brain cells, but in the tiny scaffolding inside them, structures so small they dance on the edge of the quantum world? This is the radical proposition of Orch, or a theory dreamed up by an unlikely duo, anesthesiologist Stuart Hameroff and Nobel laureate physicist Roger Penrose. Their idea hinges on microtubules, hollow protein tubes that act like the skeleton of neurons, constantly rearranging themselves to maintain the cell's shape. To most biologists, these are just cellular plumbing, but Hameroff and Penrose see them as the universe's most sophisticated quantum computers, the missing link between the mysterious collapse of quantum waves and the shimmering tapestry of human experience. Here's how it works. In the chaos of the brain, where electrical impulses fire constantly, microtubules might provide a sheltered haven for quantum coherence, a state where particles can exist in multiple positions simultaneously, like Schrödinger's cat, both alive and dead. Penrose suggests that when these superpositions become too complex, they reach a threshold and collapse, not randomly, but in a way that generates proto-conscious moments. Hameroff proposes these tiny collapses integrate across vast networks of neurons, weaving together into the seamless stream of awareness we call I. It's as if every thought is a symphony of quantum vibrations, each note played on the infinitesimal strings of microtubules. Critics, however, aren't just skeptical, they're outright dismissive. Many neuroscientists argue the brain is far too warm and wet for delicate quantum states to survive. Decoherence, the process where quantum systems get scrambled by their surroundings, should render any such effects negligible in the noisy environment of living tissue. Others point out that microtubules are present in all eukaryotic cells, not just neurons. So why aren't liver cells conscious? Even Penrose's reputation hasn't shielded Orch or from accusations of armchair speculation, with detractors like Patricia Churchland calling it quantum flapdoodle, a fancy label for wishful thinking dressed in scientific jargon. Yet the theory persists partly because it tackles gaps that mainstream neuroscience glosses over. How does the brain's wet where a lump of firing neurons give rise to the vivid redness of an apple or the ache of nostalgia? Traditional models treat consciousness as an emergent property, like traffic patterns emerging from individual cars, but Orch dares to suggest a deeper mechanism. It's a modern twist on panpsychism, where consciousness isn't magically conjured by complexity, but subtly present in the universe's most fundamental processes. Hameroff has even ventured into testable predictions. He argues that anesthetics work by disrupting quantum vibrations in microtubules, silencing consciousness while leaving non-conscious brain activity intact, a claim that, if proven, could revolutionize medicine. Meanwhile, experiments with light-sensitive algae suggest quantum effects might play roles in biological navigation, hinting that nature could indeed exploit quantum weirdness in ways we're only beginning to grasp. Whether Orch is groundbreaking or just glorified speculation, it forces us to confront the uncomfortable truth that after centuries of study, consciousness remains science's hardest problem. We can map neural pathways and correlate brain activity with emotions, but no one can explain how electrical pulses feel like anything at all. Perhaps the answer lies in quantum vibrations, or perhaps it's stranger still. But until we know for sure, theories like this remind us that reality, and our place in it, might be far more mysterious than we dare admit. Deep in the equations of particle physics lies a symmetry so beautiful, it seems the universe should obey it. A cosmic mirror where every particle we know has a hidden twin, a shadow version of itself waiting to be discovered. This is the tantalizing promise of supersymmetry, or SUSY for short, a theory that emerged in the 1970s as a potential master key to the universe's deepest secrets. The idea is deceptively simple. For every known particle, electrons, quarks, photons, there's an undiscovered superpartner lurking just beyond our current reach. Electrons would pair with selectrons, quarks with squarks, and photons with photinos. It's as if the universe runs on a kind of quantum yin and yang, with matter and force carrying particles twinned in a delicate mathematical dance. What makes supersymmetry so compelling isn't just its elegance, but the existential problems it could solve. For decades, physicists have grappled with the unsettling fact that the Higgs boson, the particle that gives others mass, is far lighter than it should be. Quantum calculations suggest its mass ought to be enormous, inflating to scales that would make atoms impossible. SUSY offers a rescue. If every particle has a superpartner, their quantum effects would perfectly cancel out these runaway values, like two opposing waves smoothing each other to stillness. Even more enticing, the lightest of these superparticles could be the mysterious dark matter that binds galaxies together, an invisible cosmic glue we've hunted for decades. Yet for all its theoretical grace, SUSY faces a glaring problem. We haven't found a shred of evidence. The Large Hadron Collider, the most powerful particle smasher ever built, was designed in part to uncover these superpartners. But after years of collisions at energies that should have conjured them into existence, the detectors remain stubbornly silent. Critics argue this absence is fatal. If supersymmetry exists, why are its particles so shy? Some theorists counter that superpartners might be heavier than expected, hiding just beyond the LHC's current reach. Others propose tweaked versions of SUSY where only certain particles have twins, or where the symmetry is broken in ways that make detection fiendishly difficult. The debate reveals a deeper tension in physics. Should we abandon ideas that fail experimental tests or cling to their beauty in hopes of future breakthroughs? Nobel winner Steven Weinberg once compared Sussy to a beautiful garden that might lie just past the next hill. But what if the hill never ends? Meanwhile, alternative theories like extra dimensions or composite Higgs models gain traction, though none yet match Sussy's explanatory sweep. What keeps Sussy alive is less hard data than sheer desperation. The standard model of particle physics, triumphant as it is, feels incomplete, a fractured mirror reflecting only part of reality. Supersymmetry promises to mend that mirror, to reveal a universe where every force and particle fits into a grand, symmetrical whole, until the next generation of colliders, or a stroke of luck, delivers answers. Sussy remains physics' most seductive mirage, a theory too perfect to ignore, yet just out of reach, whispering that the universe's deepest secrets might still be waiting in the shadows. What if space-time at the smallest scales isn't a smooth, flowing fabric, but a jumble of geometric fragments, a cosmic jigsaw puzzle where each piece is a tiny, shimmering shard of reality? This is the striking vision of causal dynamical triangulation, a bold approach to quantum gravity that trades Einstein's elegant curves for simple, angular building blocks called simplices. Picture a child's toy set where every triangle, tetrahedron, and higher dimensional shape snaps together to form the scaffolding of spacetime itself. Unlike string theory's tiny vibrating threads or loop quantum gravity's woven networks, this framework imagines the universe as a dynamic mosaic, constantly rearranging itself according to strict causal rules. The beauty of this model lies in its simplicity. By treating spacetime as a collection of these elementary shapes, each representing a minuscule chunk of reality, physicists can simulate how gravity behaves at scales far smaller than an atom. The key innovation is causality. Unlike earlier attempts where time could twist into knots, here every simplex must connect in a way that preserves the arrow of time. Imagine building a tower where each block must sit firmly on the one below it, no floating bricks, no loops, just a clear, upward progression. This constraint keeps the universe orderly, preventing paradoxes where cause and effect get tangled. Remarkably, when researchers run computer simulations of this process, letting countless simplices interact and evolve, something astonishing emerges. At large scales, the chaos smooths out into the four-dimensional spacetime we recognize, 3 dimensions of space, 1 of time. It's as if individual pixels on a screen blend into a seamless image when viewed from afar. Even more striking, the model predicts this outcome rather than assuming it, offering a rare glimpse into how dimensionality itself might arise from deeper, more fundamental rules. Yet for all its mathematical elegance, causal dynamical triangulation faces a formidable challenge. It exists almost entirely in the realm of theory. Unlike general relativity, confirmed by bending starlight, or quantum mechanics tested in countless labs, this approach lacks experimental signatures to hunt for. Some physicists argue that the Planck scale, where these geometric fragments would reveal themselves, is so inconceivably tiny that testing it directly might forever be beyond our reach. Others hold out hope for indirect clues, like subtle fingerprints in the cosmic microwave background or anomalies in high-energy particle collisions. The theory also grapples with rivals that take radically different paths. String theorists dismiss it as a crude approximation, while loop quantum gravity proponents argue that spacetime's granularity should manifest as loops, not rigid shapes. But defenders counter that by starting with such basic ingredients, no extra dimensions, no unproven particles, their model stays grounded in geometric purity. What makes this approach so compelling isn't just its answers, but the questions it forces us to ask. Could the smooth spacetime we experience really be a patchwork of quantum geometry? If so, does that mean reality has a resolution like a digital image? And if we could peer past the illusion of continuity, would we see the universe's true scaffolding, an endless dance of shapes, clicking together and apart in perfect causal rhythm. Until experiments catch up, these mysteries linger, teasing us with the possibility that beneath the universe's polished surface lies a realm of crystalline simplicity waiting to be decoded. What if the deepest truths about reality aren't found by dissecting it into smaller pieces, but by realizing there were never separate pieces to begin with? This is the radical heart of non-duality, a cornerstone of Buddhist philosophy that dissolves the boundaries we take for granted between self and world, observer and observed, even existence and emptiness. While Western science often seeks to understand the universe by breaking it down atoms, quarks, strings, non-duality points in the opposite direction, toward a wholeness so fundamental that all divisions are revealed as illusions, like waves forgetting they're made of ocean. At the core of this view sits a startling claim: the feeling of being a separate self is the root mirage. When Buddhist monks speak of no self, anatta, they aren't denying experience but pointing to the absence of an isolated controller behind it. Think of a whirlpool in a river. It has a recognizable shape, yet no essence separate from the water flowing through it. Through intensive meditation, practitioners report direct glimpses of this interconnectedness, where the sense of me and mine dissolves into boundless awareness. Modern neuroscience lends eerie support. Studies on advanced meditators show decreased activity in the default mode network, the brain region tied to ego and narrative identity. It's as if the hardware of separation softens under sustained focus. Quantum entanglement offers a tantalizing parallel. When two particles become entangled, measuring one instantly determines the state of the other, no matter the distance, a phenomenon Einstein called spooky action at a distance. This violates classical notions of locality and separateness, suggesting that at fundamental levels the universe operates as an undivided whole. Physicist David Bohm saw this as evidence of an implicate order, where apparent fragmentation is just a surface ripple over deeper unity. Buddhist non-duality and quantum physics might use different languages, but both hint at a reality where isolation is the illusion and connection the baseline truth. Yet the contrast with scientific reductionism couldn't be starker. Western empiricism often assumes reality is best understood by analyzing smaller components, cells to molecules to atoms. This approach has unlocked staggering advances, from vaccines to microchips, but it struggles with questions of meaning and subjective experience. Non-duality flips the script. Instead of building up from parts, it starts with the whole and sees divisions as provisional, like labeling patches of sunlight on a forest floor while forgetting they all come from the same sky. Critics argue this view is untestable, more mysticism than science, but advocates counter that meditative insights reproducible across cultures and millennia offer a kind of first-person data, a direct encounter with reality's seamless fabric. The implications ripple far beyond philosophy. If non-duality holds water, it reshapes how we relate to suffering: no separate self to protect, to nature no true boundary between human and ecosystem, even to time, past and future as folds in an eternal present. It's a vision both ancient and urgently modern, challenging the fragmentation driving ecological crisis and social isolation. And while science may never prove non-duality, the resonance between meditative wisdom and quantum weirdness suggests that reality, in the end, might be far stranger and far more unified than our dualistic minds can fathom. After all, if a particle can be in two places at once, who's to say you and the world were ever truly apart? What if gravity, the force that pins your feet to the ground and guides the dance of galaxies, isn't a fundamental force at all, but a side effect of something far stranger, the universe's tendency toward disorder? This is the provocative claim at the heart of emergent gravity, a theory pioneered by Dutch physicist Eric Verlin that's shaking the foundations of cosmology. Forget Newton's apple or Einstein's warped spacetime. In Verlin's vision, gravity is an illusion, a collective mirage born from the microscopic chaos of quantum information. The story begins with entropy, a concept usually associated with thermodynamics. Think of ice melting in a glass or perfume dispersing in a room. Entropy measures disorder, but in the quantum realm, it's also linked to information. Verlin's breakthrough was realizing that the way entropy changes with position could mimic gravity's pull. Imagine standing in a crowd where everyone holds a tiny piece of a puzzle. As you move, the arrangement of pieces around you shifts, creating a kind of pressure that guides your path without any force actually pushing you. In this analogy, gravity isn't a force but a statistical nudge, emerging from the universe's hidden information landscape. What makes emergent gravity so electrifying is how it tackles one of cosmology's biggest embarrassments: dark matter. For decades, astronomers have observed galaxies rotating so fast they should fling themselves apart, unless invisible matter lurks within, providing extra gravitational glue. Verlin's math offers an alternative. Maybe there's no dark matter at all. Instead, the extra pull could arise from the way entropy, and thus emergent gravity, behaves differently at galactic scales. It's as if we've been chasing a cosmic ghost when the answer was hiding in plain sight, woven into the fabric of information itself, but not everyone's convinced. Traditionalists argue Verlin's theory lacks the precise predictive power of Einstein's relativity, which has sailed through every test from GPS satellites to gravitational waves. Critics point to galaxy clusters where dark matter's gravitational fingerprints seem undeniable, or to the cosmic microwave background's patterns which align perfectly with dark matter models. Some physicists dismiss emergent gravity as elegant hand-waving, a mathematical sleight of hand that glosses over the messy details of reality. Yet the theory's allure lies in its unifying potential. By tying gravity to entropy, it whispers of deeper connections to the holographic principle, the idea that reality might be a projection from a two-dimensional surface. If gravity emerges from information, then spacetime itself could be a kind of hologram, with the universe's true workings playing out on a distant, unimaginable boundary. Whether Verlin's vision ultimately holds up or not, it forces us to rethink the most familiar force in the cosmos. After all, if gravity can emerge from chaos, what other fundamental truths might be waiting to be unraveled? The universe, it seems, still has plenty of surprises up its sleeve, and the boldest ideas often come from questioning what we think we know best. What if the future isn't just shaped by the past, but actively reaches back to reshape it? This is the mind-bending premise of retrocausality, a concept that turns our understanding of cause and effect inside out. Imagine throwing a rock into a pond, but the ripples move backward in time, altering the moment the rock left your hand. While this sounds like science fiction, quantum mechanics hints that at the smallest scales, time might not be the one-way street we experience. The evidence starts with the delayed choice quantum eraser experiment, a twist on the classic double-slit setup. When particles like photons are fired at a barrier with two slits, they create an interference pattern, as if each particle passes through both slits simultaneously. But if you place detectors to observe which slit a photon takes, the interference vanishes. Here's the twist: in the delayed choice version, scientists wait until after the photon has passed the slits, but before it hits the final screen, to decide whether to look or not. Astonishingly, the photon's behavior seems to retroactively change based on that future choice. It's as if the particle knows whether its path will be observed and adjusts its past actions accordingly. Yakir Aharonov's work on weak measurements adds another layer. By delicately probing quantum systems without fully collapsing their wave functions, his team found particles exhibiting properties that appear to be influenced by future interactions. Picture a ship's wake not just trailing behind it, but also subtly shaping the path the ship took before it sailed. Aharonov's formalism suggests that quantum states are shaped by both past and future boundary conditions, a two-way dialogue across time. The philosophical implications are staggering. If the future can whisper to the past, does determinism crumble? Or does it mean the universe is even more predetermined, with the future already written in a way that constrains earlier events? Some interpretations propose a block universe where time is an illusion, and retrocausality is just our limited perspective on a static, four-dimensional tapestry. Others suggest a cosmic feedback loop where causality isn't a chain but a web of interconnected moments, each tugging on the others. Critics argue these effects are just mathematical quirks, that retrocausality conflates correlation with metaphysical influence. After all, quantum mechanics is notoriously counterintuitive, and our language might not yet have the tools to describe its nuances. Yet the experiments persist, poking holes in our classical intuition. If retrocausality holds, it could revolutionize everything from quantum computing by harnessing future-dependent states to our very notion of free will. Are we making choices, or are those choices future and past echoing through time to shape us? The answer might be both, neither, or something stranger still. One thing's certain, in a retrocausal universe, the arrow of time isn't just broken, it's doing loop-the-loops. What if quantum particles don't need an observer to collapse from ghostly superposition into definite states? What if reality solidifies all on its own? This is the spine-tingling proposition of objective collapse theories, which replace the mysterious measurement problem with a bold new rule. Wave functions spontaneously collapse after reaching a certain size or complexity. No conscious observers required. Imagine a universe where Schrödinger's cat isn't hovering between life and death because someone opens the box, but because nature itself has a built-in timer, ticking down until reality decides. The most famous of these models is the Garade-Rimini-Weber theory, or JRW, proposed in the 1980s. It introduces a mathematical tweak to quantum mechanics. Every particle has a tiny but non-zero chance to suddenly localize, snapping from a spread-out probability wave to a definite position like a cosmic game of musical chairs. For single particles, this happens extremely rarely, maybe once every 100 million years. But in large objects like cats or lab equipment, which contain countless particles, the chances multiply until collapse becomes inevitable. It's as if reality has a hidden failsafe, ensuring that macroscopic things stay concrete while permitting quantum weirdness in the microscopic shadows. This approach elegantly sidesteps the thorny question of why observation matters in quantum mechanics. No more wrestling with Wigner's friend or pondering whether cameras count as observers. Instead, GRW offers a clean mechanical process. Hit a threshold and boom, reality crystallizes. Supporters argue this restores objectivity to physics, scrubbing away the anthropocentric stain of consciousness-driven collapse. Experiments with nanoscale cantilevers and supercooled molecules have even sought evidence for such spontaneous localization, though results remain inconclusive. Yet the theory opens its own Pandora's box. If wave functions collapse spontaneously, what triggers the exact threshold? Why do particles in a diamond stay coherent for lab experiments while those in dust motes don't? Critics like Roger Penrose propose a wild alternative. Gravity might be the hidden hand. His gravitational objective reduction suggests that when quantum superpositions become too massive, space-time itself can't tolerate the strain and forces a collapse. Picture a bridge buckling under too much weight, except the bridge is the fabric of reality, and the weight is a particle's split identity. The debate between observer-driven and objective collapse isn't just academic, it reshapes how we view reality seems. One camp sees consciousness as the ultimate architect, the other paints a universe running on autopilot. But perhaps the most unsettling question isn't which model is right, but whether the answer lies hidden in the cracks between them, waiting for a deeper theory to emerge. After all, if quantum mechanics has taught us anything, it's that reality rarely follows the scripts we write for it. What if the universe runs not on atoms or energy, but on something far more ethereal, pure information? This radical idea transforms matter into a secondary effect, a kind of cosmic afterthought emerging from a deeper layer of bits and codes. At its heart lies John Wheeler's provocative phrase, "it from bit," a declaration that every particle, every force, every flicker of existence might ultimately boil down to yes-no answers, a universe built not from stuff but from decisions. Wheeler, the visionary physicist who helped shape quantum theory, saw information as the ultimate bedrock. Imagine reality as an endless cosmic questionnaire where each quantum event, a photon's path, an electron's spin, isn't just measured but defined by the act of questioning. In this view, the universe isn't a machine grinding along deterministic tracks. It's a participatory network, a vast dialogue where observation doesn't just reveal reality but actively generates it. It's as if the cosmos is a grand simulation, not in the silicon and code sense, but in the way every interaction computes itself into being. This perspective dovetails eerily with digital physics, where the universe operates like a colossal, self-executing algorithm. Think of the double-slit experiment. A particle behaves as a wave until observed, collapsing into a definite state. Digital physics interprets this as a rendering process, like a video game, only drawing the trees you're looking at to save processing power. Even black holes, those infamous cosmic shredders, might preserve information rather than destroy it, encoding whatever falls in onto their event horizons like celestial hard drives. The holographic principle takes this further, suggesting the three-dimensional world we experience is a projection from a two-dimensional surface where information is stored, like a movie playing out on the surface of a DVD. But how could abstract information conjure up the solidity of a rock or the warmth of sunlight? Consider how a DNA strand, a string of molecular letters, can blueprint an entire organism. The information isn't just describing the organism, it's orchestrating its construction. Scale this up, and perhaps the universe's laws are similarly algorithmic, with particles as tokens in a cosmic computation. Critics argue this reduces physics to metaphysics. How do you test whether a quark is really information? Yet experiments like quantum entanglement, where particles instantly influence each other across vast distances, hint at a reality where connections transcend physical proximity, aligning with information-based models. The stakes couldn't be higher. If information is primordial, it redefines what we are. Your thoughts, memories, even the sensation of being you might not be emergent properties of neurons firing, but patterns in a universal data stream. It's a humbling, exhilarating thought that beneath the whirl of galaxies and the pulse of living cells, the cosmos might be whispering to itself in binary, each bit a brushstroke in a masterpiece we're only beginning to decode. What if the cosmos isn't sculpted by gravity alone, but by vast, invisible rivers of electrified gas, a universe humming with currents we've barely begun to map? This is the electrifying vision of plasma cosmology, championed by Nobel laureate Hans Alfvén, who dared to challenge the Big Bang with a radical alternative: that 99% of the observable universe isn't made of inert matter, but ionized plasma threaded by electromagnetic forces powerful enough to shape galaxies. Forget dark matter and singularities. Alfvén's cosmos crackles with cosmic lightning, where filaments of charged particles stretch across millions of light years, weaving structures in ways gravity never could. Alfvén's work began with the humble tokamak, a donut-shaped device used to study nuclear fusion. Observing how plasma's superheated gases where electrons roam free formed intricate filaments and cells, he realized something astonishing. The same patterns appeared in deep space imagery. Galactic arms, comet tails, even the vast voids between galaxy clusters seem to mirror the behavior of plasma in labs, as if the universe were a scaled-up version of these electromagnetic dances. He proposed that these forces, not just gravity, could explain cosmic jets spewing from quasars or the perplexing rotation curves of spiral galaxies that later sparked the dark matter hypothesis. The implications are staggering. Plasma cosmology suggests that galaxies might form along colossal, twisting currents called Birkeland filaments named after Christian Birkeland, who first theorized their earthly counterparts as the cause of auroras. Picture the Milky Way not as an island drifting in emptiness, but as a knot in a glowing web of electromagnetic energy, connected to other galaxies by unseen power lines crackling with charge. Even the famed cosmic microwave background, often hailed as the Big Bang's afterglow, could be reinterpreted as the thermal imprint of plasma oscillations in our local galactic neighborhood. Yet mainstream cosmology largely dismisses these ideas. The Big Bang model, with its inflationary expansion and dark energy, remains the dominant paradigm, bolstered by precise measurements of the cosmic microwave background's uniformity, a hallmark of early rapid expansion. Critics argue that plasma cosmology fails to explain this uniformity or the abundance of light elements like helium, which the Big Bang accounts for neatly. Worse, Alfvén's theories often rely on phenomena observed in lab plasmas but not conclusively detected at intergalactic scales, leaving them in the realm of intriguing speculation. But plasma cosmology's rebels aren't silenced. They point to anomalies like the axis of evil, a mysterious alignment of cosmic microwave background fluctuations that defies standard models, or the perplexing coherence of galactic magnetic fields, which seem too vast and organized for gravity alone to explain. Some even suggest that dark matter's gravitational effects could be illusions created by the collective pull of these unseen electromagnetic structures. Whether Alfvén's vision ultimately holds or not, it forces us to confront an uncomfortable truth. We've barely scratched the surface of the universe's full toolkit. Just as Einstein revealed gravity as warped spacetime, not just Newton's pull, perhaps electromagnetism's cosmic role is far grander than we've dared to imagine. After all, if the night sky is threaded with invisible currents, what other forces might be hiding in plain sight, waiting to rewrite our maps of reality? What if our universe is just one slice in a cosmic loaf of bread, floating alongside countless others in a hidden dimension we can't perceive? This is the startling premise of brain cosmology, where our entire reality might exist as a three-dimensional membrane, or brain, drifting in a higher dimensional space. Unlike traditional models that treat the universe as self-contained, this theory suggests we're embedded in something far grander, like a sheet of paper suspended in a vast, multidimensional void. The idea emerges from string theory, which requires at least 10 dimensions for its equations to work. While we experience only 3 of space and 1 of time, the rest could be compactified, curled up so tiny we'd never notice, or they might stretch far beyond our brain's boundaries. Physicists Lisa Randall and Raman Sundram turbocharged this concept with their groundbreaking models in the late 1990s. They proposed that gravity, unlike other forces, isn't confined to our brain but leaks into the bulk, the higher dimensional space beyond. This leakage could explain gravity's puzzling weakness compared to other forces. It's not inherently feeble, just diluted across dimensions we can't access. Imagine ants crawling on a bedsheet suspended in a breeze. They'd perceive only the sheet's surface, unaware of the air around it or the hands that might shake it. Now picture that sheet rippling not from wind, but from collisions with other brains. Some theorists suggest the Big Bang itself could have been such a collision, an unimaginable smash-up between our brain and a neighboring one, seeding our universe with energy. Even more intriguing, these higher dimensional interactions might leave detectable traces. When black holes merge, the gravitational waves they produce could carry fingerprints of extra dimensions, subtle distortions in the space-time ripples that betray the hidden architecture of reality. Experimentalists are already hunting for these clues. The LIGO Observatory, which made history by detecting gravitational waves, could potentially spot anomalies in wave patterns that hint at dimensions beyond our own. Particle colliders like the Large Hadron Collider might uncover evidence of microscopic black holes evaporating into higher dimensions, or exotic particles that occasionally tunnel between brains. Even the cosmic microwave background, the afterglow of the Big Bang, might bear imprints of brain collisions like echoes from a distant, multidimensional shore. Yet brain cosmology isn't without its skeptics. Critics argue that without direct evidence, it remains elegant speculation, a mathematical sandcastle that could vanish with the next experimental tide. Others question how testable these ideas truly are, given the energy scales involved. But supporters counter that every revolution in physics began with seemingly outlandish proposals. After all, black holes and gravitational waves were once deemed too bizarre to exist until technology caught up with theory. What makes brain cosmology so captivating isn't just its scientific audacity, but its philosophical heft. If true, it would mean our universe is both vast and profoundly limited, a single page in a book we can't yet read. And somewhere beyond our perceptual reach, other brains might hover, their own histories unfolding in parallel, their stars and civilizations forever separated by dimensions we can't cross. The night sky would become not just a window to distant worlds, but a mirror reflecting the edges of our cosmic prison, and perhaps, if we look closely enough, the faintest glimmers of what lies beyond. Ever wonder why the quantum realm's bizarre blur of possibilities solidifies into the crisp, predictable world we navigate daily? Why don't we see cats simultaneously dead and alive, or chairs hovering in superposition? Enter quantum Darwinism, a theory that doesn't just explain this transition. It reveals it as a cosmic game of survival, where only the most resilient quantum states make it into our classical reality. At the heart of this idea is physicist Wojciech, who proposed that the environment itself acts as a relentless editor, amplifying certain quantum states while erasing others until only the fittest remain. Imagine tossing a pebble into a pond. The ripples don't just vanish, they spread, interact with leaves and twigs, and leave imprints on the water's surface. In Juk's framework, quantum systems behave similarly. When a particle exists in multiple states at once, say, spinning both clockwise and counterclockwise, it doesn't stay isolated. It interacts with its surroundings, air molecules, photons, even the faintest cosmic rays. These interactions copy specific aspects of the particle's state into the environment over and over, like countless witnesses recording the same event. Over time, only the states robust enough to withstand this copying process persist, while the others fade into oblivion. This is the essence of quantum Darwinism. The environment selects which quantum states become classical reality, much like natural selection favors traits that survive reproduction. Take Schrödinger's infamous cat. In the quantum realm, the cat could indeed be both dead and alive, until the box interacts with the outside world. Photons bouncing off the cat, air molecules touching its fur, even the vibrations of the box's walls all measure its state, creating countless copies of a single outcome in the environment. By the time you open the box, the system has reached quantum consensus. The environment unanimously agrees on the cat's fate, leaving no trace of the other possibility. This isn't magic. It's physics playing out in trillions of tiny interactions, each one a vote in reality's ledger. Juk's theory also solves the preferred basis problem, why we observe particles in specific states position, momentum rather than unpredictable superpositions. The answer lies in pointer states, quantum configurations stable enough to withstand environmental scrutiny. Think of them as the universe's default settings, the forms matter naturally prefers when bombarded by reality's chaos. A spinning top might wobble, but its pointer state is upright rotation. Any quantum equivalent of a wobble gets erased by the environment's relentless copying. Critics argue this merely shifts the mystery from observers to environments. Why does interaction collapse wave functions, yet experiments support Jerk's vision? In labs, quantum systems do decohere, lose superposition faster when exposed to noise, much like Darwinian selection pressures. Even the cosmic microwave background, the oldest light in the universe, could be seen as a fossil record of quantum states that, 1. The early cosmos's decoherence lottery. The implications ripple far beyond physics. If quantum Darwinism holds, objectivity itself emerges from consensus, not from some pristine Platonic realm, but from countless tiny agreements between systems and their surroundings. Reality isn't handed down from on high, it's negotiated moment by moment in the quiet chatter of particles and photons. And that's the true elegance of this theory. It doesn't just bridge quantum weirdness with everyday experience, it shows how the latter grows from the former, like a tree rising from the chaos of microscopic roots. What if the universe, in all its apparent chaos, is secretly unfolding from an invisible, deeper order, a hidden harmony where every event, every particle, is intimately connected in ways our senses can't perceive? This is the mesmerizing vision of David Bohm's implicate order, a radical reimagining of reality that challenges the fragmented, billiard ball universe of classical physics. Bohm, a protege of Einstein and one of quantum theory's most original thinkers, refused to accept that particles magically choose their states when observed, a cornerstone of the Copenhagen interpretation. Instead, he proposed that the quantum world's strangeness hints at a vast, unbroken wholeness beneath the surface, like an infinite origami where every fold contains the entire cosmos. At the heart of Bohm's model is pilot wave theory, an alternative to mainstream quantum mechanics. Picture a surfer riding a wave. The particle, the surfer, is guided by an unseen, deterministic field, the wave, which dictates its path. Unlike the Copenhagen view, where particles lack definite properties until measured, Bohm's hidden variables ensure everything has real, well-defined positions at all times, just governed by a deeper, non-local influence. This elegantly explains quantum weirdness like the double-slit experiment. The particle moves through one slit, but the pilot wave passes through both, creating interference that steers the particle's trajectory. No ghostly collapses, no observer dependence, just a hidden choreography guiding the dance. But Bohm didn't stop there. He saw pilot wave theory as a shadow of something grander, the implicate order. Imagine a hologram where every fragment contains the whole image just from a different angle. In Bohm's cosmos, the visible world, the explicate order, is like the hologram's projected image, while the implicate order is the underlying interference patterns holding it all together. Time and space aren't fundamental, they're emergent like ripples on a pond. A particle here and a galaxy there might seem separate, but at the implicate level, they're enfolded into a single, undivided reality. This idea resonates eerily with quantum non-locality, the phenomenon where entangled particles instantly mirror each other's states, no matter the distance. For Bohm, this wasn't spooky action at a distance but evidence of the implicate order's unity. Like two whirlpools in a shared river, the particles appear separate, yet their movements are synchronized by the deeper current. Critics dismissed this as metaphysical hand-waving, especially when experiments confirmed non-locality but couldn't distinguish Bohm's model from standard quantum theory. Yet his framework offers something the Copenhagen interpretation lacks, a visualizable reality, free of paradoxes where observation creates existence ex nihilo. Bohm's ideas found unexpected allies in Eastern philosophy. He corresponded with Jiddu Krishnamurti, exploring parallels between the implicate order and Buddhist notions of interdependence. Both saw fragmentation as illusion, the mind carving divisions into a seamless whole. Modern science, too, hints at Bohm's vision. The holographic principle in string theory suggests our 3D universe might be projected from a 2D boundary, echoing his enfolded reality. Even neural networks, where simple nodes give rise to complex behaviors, mirror his belief that simplicity underlies apparent complexity, yet the implicate order remains controversial. Detractors argue it's untestable, adding hidden layers without predictive power. Why invent an invisible matrix when standard quantum math works flawlessly? Others counter that science has always progressed by probing the unseen, from atoms to dark matter. Perhaps Bohm's greatest legacy is his challenge to reductionism, his insistence that the universe isn't just pieces to dissect, but a dynamic, interconnected process. In a world straining under ecological and social fragmentation, his call to perceive wholeness feels less like physics and more like prophecy. After all, if reality truly is a cosmic hologram, then every act of observation isn't just seeing, it's unfolding. What if the universe operates not by familiar forces like gravity or electromagnetism, but through an invisible geometric code, a set of mathematical rules so fundamental they rewrite physics from the ground up? This is the audacious claim of null physics, a fringe theory that dismisses mainstream cosmology in favor of a radical new framework built not on particles or quantum fields, but on pure geometric axioms. Its creator, physicist Terence Witt, argues that decades of equations chasing dark matter, inflationary expansion, and even the Big Bang itself are red herrings, distractions from a deeper truth hidden in the symmetries of abstract shapes. At its core, null physics proposes that reality emerges from two primordial geometric forms, the helix and the sphere. Witt's equations suggest these shapes interact to generate all known forces and particles through their dynamic relationships, like cosmic origami folding into existence. Gravity isn't a warping of spacetime, but a geometric artifact, a side effect of helical structures, unwinding at cosmic scales. Even time itself becomes an illusion, a perceptual byproduct of these geometric transformations. The theory's elegance lies in its economy, where the standard model requires dozens of particles and arbitrary constants. Null physics aims to derive everything from first principles, like a grand unified theory written in the language of geometry. Yet for all its boldness, the theory exists in a kind of academic limbo. Peer-reviewed journals have largely rejected Witt's work, citing a lack of testable predictions and mathematical inconsistencies. Critics compare it to a Rube Goldberg machine, creatively elaborate but functionally implausible. Without empirical evidence, null physics struggles to gain traction, remaining a thought experiment rather than a working model. Mainstream physicists point to overwhelming evidence for cosmic inflation, dark matter's gravitational fingerprints, and quantum entanglement phenomena which geometric axioms fail to address convincingly. The tension here reflects a deeper divide in science. Should elegance and intuition drive theory, or must all ideas bow to experimental verification? History offers cautionary tales on both sides. Einstein's general relativity was once deemed too abstract, yet its predictions about bent starlight were confirmed. Conversely, countless beautiful theories have evaporated under scrutiny. Null physics sits uncomfortably between these poles, a geometric daydream awaiting either validation or oblivion. Perhaps the theory's greatest value lies in its defiance. By questioning foundational assumptions, it pushes physicists to articulate why their models work, or why alternatives don't. In a field where dark matter remains elusive and quantum gravity unsettled, even fringe ideas can sharpen the debate. After all, today's heresy sometimes becomes tomorrow's textbook chapter, if it survives the forge of evidence. Until then, null physics stands as a geometric castle in the clouds, its spires towering over a landscape it might never touch. From simulated realities to cosmic holograms, from branching multiverses to timeless blocks where past and future eternally coexist, we've journeyed through ideas so wild they don't just bend the rules of reality, they shatter them entirely. Think about it, the ground beneath your feet might be an illusion, a fleeting projection from the edge of space. Your choices could be spawning infinite alternate versions of yourself right now, living out every possible path. Even time itself, that steady drumbeat of existence, might be nothing more than a trick of perspective, a flickering shadow cast by a deeper, unchanging structure. These theories aren't just science fiction, they're the cutting edge of human curiosity, where physicists and philosophers stare into the abyss of the unknown and dare to imagine what stares back. Some ideas, like the holographic principle or quantum Darwinism, emerge from rigorous math and lab experiments. Others, like Boltzmann Brains or retrocausality, feel like brain-twisting paradoxes designed to humble us. Yet each one, no matter how outlandish, forces us to confront the same unnerving truth. Reality is far weirder, more fluid, and more mysterious than our everyday senses suggest. So, which of these mind-melting concepts left you reeling? Was it the eerie elegance of the mathematical universe, where existence itself is just an equation solving itself? Or the haunting thought that you might be alone in a solipsistic dream, conjuring galaxies and history from nothing? Maybe it's the visceral thrill of black hole cosmology, the idea that our universe is just the cosmic debris of a long-dead star's collapse. Whatever stuck with you, that's the magic of this quest. Theories like these don't just expand our knowledge, they rewire our sense of wonder. The adventure doesn't end here. Every week, scientists edge closer to breakthroughs that could confirm or obliterate these visions of reality. To stay ahead of the curve, hit that subscribe button and join us as we unravel more of the cosmos' greatest mysteries. And don't forget to drop a comment below. Which theory shattered your understanding of existence? The conversation is just beginning, and the universe, whatever it truly is, has plenty more secrets.